So these are introductory questions associated with the Math Skills 3 applications of linear function examples. I want to make these a separate video so you guys can look at those, and then if you need to look at the breaking examples or the other examples separately, you just talk about those. So this may not be the most entertaining part of the video, as if the other parts are, and probably I should have done this a more complicated way, but basically before we start using them, we just want to talk about how do engineers use mathematical functions. Well, we know we use math a lot. We talk about it all the time in engineering, but how do we use them? Well, we use them to explain real-world problems, to describe, and I use real-world problems. So what do I mean by real-world problems? So we use some sort of function that models what happens in the real world. That you might have a function that looks something like f of x equals 3x. Okay? Some straight line, no problems. Oh, or maybe it's squared in this case. Or maybe we get more complicated terms. Put some e's in there, or put a sine function in there. Whatever it is, we get more and more complicated as things go on, and as you go on in your engineering career here, you're going to find things that get more complicated. But whether it's simple things today where we're going to talk about where we model things to be straight lines, or we get something really complicated like that, basically we're just finding a way to describe something that's out there in the world in a mathematical way to make it easier to deal with. And we use things like, in a function, we have different definitions of things. So x we talk about here would be our independent variable. So that's what we usually think is the thing that we're looking at, or the thing that we're measuring, or the things that we can observe to start with, and we want to see. So that's our independent. How does it affect something else? That's what we call our dependent variable. And so another way of thinking about this is the cause. That's the effect. Where this is the input, that's the output. That we have these so a general relationship between the independent and the dependent is the independent is the cause and the dependent is the effect. Sometimes you'll see functions written where we think that might be backwards. We'll see one of those in the examples later. It's just a lot of it comes down to the way you're thinking about things. And as I said, they can get very complicated, or it can be fairly simple, like the ones we'll deal with today. So how do we develop these mathematical functions? Well, several different things can go into that, and I probably should have found a better place to write on than on this small sheet of paper. But we can rely on things like expert opinions. We can collect data. Or we can use scientific laws. Some combination of that are generally how we decide what function might fit this best. We may just collect a bunch of data, find a curve that fits it, and not really have any principles behind why the data fits that until we start working with it later and maybe discover what that is. Other times we start from things we know in the world about gravity or something like that. We know how gravity affects things. We know acceleration caused due to gravity. We use that a lot of times to describe things. You probably did that at some point in your time before when we start talking about quadratic functions. You have the problem that comes up all the time of an object launched upward, and you use initial velocity comes into play in one place. The acceleration due to gravity comes into place in another. And so all those things come into it. And we can make it really complicated by adding things in like drag and wind speed, and things can make our model more complicated. But normally we're going back and relying, at least on some level, into what experts in the field know, how we were able to collect some data, or some scientific laws. And the good part for us right now is we're just trying to learn how to work with the functions. We're not trying to completely develop them. So that's developing them. That's for a later course. You may do those at another time. What we want to know is we've already got equations like this developed. how do we use it? And then, so the third part is how do we communicate mathematical functions? Well, one is we have equations. And like right down here, we see in the first example, there's this equation that describes velocity versus time. We'll talk more about it when we get there. But we have equations, and generally, those are good for talking to other engineers or scientists or mathematicians. Those people love seeing equations. They can see an equation and understand what all's going on there. For other people that aren't well versed in mathematics or interested in mathematics, a lot of times what we do is create meaningful graphs. And we'll talk more in these examples about what do we mean by meaningful, but mainly it has to be accessible to others. That your grandma can look at that and have some idea of what's going on by looking at that graph. She may not understand all the science behind it, but she can look and see, oh, so as you go further in time, we get less velocity. It's slowing down. Yeah. So and it's easily correlated with what they expect to see in the real world. Things like that. And so to make them meaningful, we got to do important things like label them. What are the units on these things? What is the slope, perhaps? Where does it intercept? What happens when it's zero? Things like that. And we'll talk about exactly what goes into that. But graphs are usually how we send things out into the general community.